This is Cogitations with Carl Hartman, minister at Main Street Church of Christ in Lockney.
Good morning. Glad you're up and moving and have tuned in to 106.1 The Flip FM for our next segment of Cogitations. We're going to continue pressing forward in our examination of our origin and answering the question, how can I know? How can I know with the utmost degree of certainty how this entire universe came to be? And what is the only answer that ultimately stands the scientific test of not being able to be disproven by existing fact and theories? Oh, I'm sorry, not theories, facts and laws. Remember, theories are the best guesses. But as we get more data, those theories change and alternate. And we examined that last Sunday towards the end when we really looked at, is matter or is energy the answer, the cause for the effect that we observe as the universe? And we dismantled how those cannot be the answer, thus destroying the old theory of evolution, which changed because they determined matter's not eternal. Matter can be utterly destroyed and done away with. That old thought process of the conservation of matter, that's been annihilated. And so they moved and changed their theory to energy, but we've unraveled that as well because energy cannot exist without matter pre-existing it, because that destruction of that matter, the consumption of that matter, produces energy. So you can't have a point of energy without matter preceding that point of energy. And since they've already determined matter is not eternal, the source of energy, you can't have energy. So let's move on, and we're going to get into some really deep water. So hopefully you have your thinking cap nearby and you can snug that on your head and be ready to just kind of follow along and absorb some information, because there's some things that we need to clearly understand. And we're going to get into the laws of thermodynamics. I know you didn't wake up this morning ready for more of a science lesson, but ultimately we're getting to how we can observe, just like we read last week in Romans 1:18 and following, and there in Psalms 19, God himself indicated in his inspired word that we can come to know that he exists without the Bible, but by observing creation. Creation itself, as the psalmist said, speaks to us, reveals, as Paul said in Romans, reveals the invisible attributes of God. So in order to alleviate confusion, scientists discuss thermodynamic values in reference to a system or the surroundings. Now, there are a lot of terms we need to come to understand, because if you don't operate in the scientific world, then you read these laws and you don't understand what that law is really talking about, because you don't understand all the terms in there. Everything that is not a part of the system constitutes the surrounding. So you have the system and you have the surroundings. The system and surroundings are separated by a boundary. For example, if the system is 1 mole of a gas in a container, then the boundary is simply the inner wall of the container itself. Everything outside of the boundary is considered the surroundings, which would include the container itself. The boundary must be clearly defined so one can clearly say whether a given part of the world is in the system or in the surroundings. If matter is not able to pass across the boundary, then the system is said to be closed. Otherwise, it's open. So your system is either closed or open, and that's defined by the ability of matter to pass through the boundary. So it's like standing at the side of your house with a tennis ball, throwing it against the brick wall. The interior of your house is one system. The boundary of the house is the outer walls of the house. The tennis ball is incapable of passing through. The matter that comprises the tennis ball does not pass through that boundary. Now, we could take that to obscene levels and drive a semi through your boundary, right? But we're not talking about breaking the boundary. We're just talking about being able to pass through. Take our atmosphere. Our atmosphere stops a lot of gases from leaving. Our atmosphere stops a lot of harmful energy that's radiated from the sun and other sources from coming in, but a meteorite's going to go through our atmosphere. Spaceships go out and back in through our atmosphere. So it's a boundary, but it's an open boundary because it doesn't stop matter. So remember these terms, closed and open. Very important. A closed system may still exchange energy with the surroundings unless the system is an isolated one. So we have closed, open, isolated, in which case neither matter nor energy can pass across the boundary. So a closed, a matter can't pass through, but energy and stuff can. Open, matter passes through. Isolated, neither matter nor energy passes through. Now, I got all of this out of Boundless, the 3 laws of thermodynamics, Boundless Chemistry, and it was published 21 July 2015. So, again, another science book gives us these good definitions, closed, open, and isolated system. And a lot of what we're going to look through is confined in that writing on the 3 laws of thermodynamics. So let's begin to examine these laws of thermodynamics and how they relate. And what a lot of people don't realize, we got the 3 laws of thermodynamics. They've actually had to backpedal and have a 0 law that precedes it. But let's understand some things and how these apply to us. The first law of thermodynamics states, in a version of the law of conservation of energy adapted for thermodynamic systems, the law of conservation of energy states that the total energy, note this, of an isolated system is constant. Energy cannot be transformed from one form to another, but cannot be created or destroyed. So the energy can be transformed, but not created or destroyed. But here's the thing. That's only in an isolated system. That is only in something in which energy and matter cannot pass the boundary. So therefore, there's nowhere for the energy to radiate to go, to be dispensed to. The energy is trapped within that container. Now, where in the universe, outside of a lab, do we actually observe an isolated system? Right? You might have that brick fireplace at your house, and you build a big, huge fire in that brick fireplace. Let that fire burn for like an hour. Go outside and touch the bricks on the back of the fireplace on the outside, and you're going to feel what? Heat, warmth. Even the bricks, while they may slow the radiating of that energy through the brick walls of the fireplace, it doesn't stop the energy from ultimately transferring through and that heat coming to the outside. So our universe does not have an isolated system. So fundamentally, this first law that talks about how energy is constant doesn't apply to our universe. The sun burns fuel, generates heat. That heat radiates out across our entire solar system. It penetrates through our atmosphere, through that boundary, to the planet. It's not an isolated system. It's not an isolated system. So the first law doesn't really apply. Second law, that the entropy, this is really the striving for equilibrium, the entropy of an isolated system, not in thermal equilibrium, almost always increases. But again, we're dealing with an isolated system. Third law, entropy of a system. Okay, a system. We go back and we understand the definition of a system, right? A system consists of its surrounding. The system and surrounding are separated by a boundary. So everything within a system, doesn't matter what the boundary is. It doesn't have to be an isolated boundary. It could be a closed or an open boundary. All right. So everything in a system, entropy of a system approaches a constant value as the temperature approaches absolute zero. Okay. And absolute zero is a really big negative number. All right. So the entropy of a system approaches a constant value. Now, when heat is being moved through a system, and that's what heat's trying to do. Heat is trying to bring everything to the same equal temperature. When that temperature approaches absolute zero, when it actually reaches absolute zero, everything stops moving. Everything stops moving. That's why thermodynamics is so important, because thermodynamics is the movement of the entire universe. I mean, when we move, our body produces heat. The more we move, the more heat it produces. Then the body tries to cool itself by sweating, right? And so we have this system that is trying to reach entropy, reach absolute zero. But at that point, everything is going to cease, is going to stop. So let's move forward and exploring this a little bit more and understanding. But what about the laws of thermodynamics? With entropy, what is it? What's its real implication? What is entropy? Okay, we may not fully understand what that is. The level of disorder in the universe is steadily increasing. See, our universe started as a system that was in order. And as things continue to move, things continue to lose mass that are energy sources such as the sun, we are moving more and more to disorder. Systems tend to move from ordered behavior to more random behavior. You can just think of a mechanical wheel that spins. And when it's first built and designed with precision, it runs with precision. But over time, the gears and the mechanisms, they get worn down, and you begin to get random turbulence and random behaviors within that rotating device. One implication of the second law is that heat flows spontaneously from a hotter region to a cooler region, but will not flow spontaneously the other way. We see that a lot in our meteorology and how fronts move. And so heat tries to bring everything to balance. Now, that's in an isolated system, but even outside of that, we observe the same thing. Heat moves from hot area to cold area because it's trying to bring everything to balance. This applies to anything that flows. It will naturally flow downhill rather than uphill. A pendulum will gradually lose energy and come to a stop, but it doesn't pick up energy spontaneously. We've all seen, maybe in someone's office or at some novelty shop, that little framework that has 4 or 5, I think maybe 5 metal balls hanging down. You pick one up on one end, you drop it, it hits that ball, it transfers the energy through, and the one on the other side moves, and the pendulum goes, transferring energy through those balls with every strike. But what ultimately happens, unless you intervene and grab one of them again and drop it again, it eventually stops. The energy, the flow of energy ceases. So a pendulum will gradually lose energy and come to a stop, but it doesn't pick up energy spontaneously. An ice cube melts to form a puddle, but a puddle never spontaneously transforms itself into an ice cube. A glass falls off a table, might shatter when it hits the ground, but the pieces will never spontaneously jump back together to form the glass again. Many processes are irreversible, and any irreversible process increases the level of disorder. One of the most important implications of the second law is that it indicates which way time goes. Time naturally flows in a way that increases disorder. The second law also predicts the end of the universe. It implies that the universe will end in a heat death. Anything in a system is going to come to a heat death in which everything is at the same temperature. We observe that in the third law as well, the third law that applies to systems. Everything is trying to reach the same temperature. Now, they have observed this practice within an isolated system, but as we saw in the third law previously, it expands to just any system. This is the ultimate level of disorder. If everything is at the same temperature, no work can be done, and all the energy will end up as the random motion of atoms and molecules. That comes from physics.bu.edu. So you can just go to that college's website and read about how this works. physics.bu.edu. As we continue, spontaneous, performed or occurring as a result of a sudden inner impulse or inclination and without premeditation or external stimulus. That's spontaneous, and nothing happens that way. Performed or occurred as a result of a sudden inner impulse. A rock is not going to have a sudden inner impulse to turn into something else. It could turn into melted rock, into lava, but you have to have an extreme heat source applied to it. It will not, in and of itself, spontaneously do anything. A rock is not going to suddenly find itself thrown out into the ocean of its own disposition. Somebody has to pick it up and throw it. It doesn't have an inclination without premeditation or external stimuli. External. Random motion of atoms and molecules, diffusion as it's called in the scientific community, ends in dynamic equilibrium. Everything is in perfect balance. There's no more flow. There's no more movement because there's no more high ground and low ground. There's no more hot and cold. Everything has come to equilibrium. Dynamic equilibrium in physics means forces are in balance. The net force should be or comes to zero. In other words, nothing is moving. Our entire solar system, our entire universe is in constant motion. But that motion is winding down. The Earth spins on its axis, but it's actually slowing down ever so slightly. We're in a brand new year. We're towards the end of the first month of this brand new year, but this time last year, the Earth was spinning just a little bit faster. It's the same thing in our movement around the sun. We're moving a little bit slower. It takes us a little bit longer. Almost unrecognizable in our lifetime. But scientists measured, and in fact, there was a contemplation not too long ago about changing our time a little bit because of so much time that we have lost because of slowing down. The moon gets a little bit further away from our planet, probably due to gravitational forces, because as we slow down, they believe that affects the gravitational force on the moon. And so on average, it moves an inch every year away from the Earth. See, we're moving to this disorder. But what about the laws of thermodynamics? In our universe, we have what's called a heat bath of photons. These are the cosmic microwave background photons at a temperature of 2.78 Kelvin. That's a pretty cold heat bath. I don't want to bathe in that heat bath. I like a hot bath. And obviously, you and I and the sun are much hotter. So we're not in equilibrium with the heat bath of the universe. But over time, as the sun burns hydrogen and as planets collide and break apart and as particles decay and so on, everything eventually ends up as photons or other elementary particles, which eventually come to equilibrium. This is the conversion to heat. Our universe is marching ever slowly towards equilibrium. This is talked about by Brent Nelson, M.A. in physics, Ph.D. student at UC Berkeley, and I got this a while ago, so he probably already has his Ph.D., so if you do, congratulations, Dr. Nelson. But it was on www.physlink.com/education/askexperts/AE261.CFM. And so again, scientists understand this heat bath and what our universe is moving towards, from an ordered beginning to a disordered end, to ultimate equilibrium that we're moving ever so slowly towards. Consider the case when two atoms undergo a nuclear reaction and give off energy, something similar to a nuclear bomb or a reaction in a nuclear reactor. The matter, of the products is less than what was started with. Mass has been lost. This is because the lost mass has been changed into energy. Again, Mr. Nelson shares that information with us, that same location. So it's like a log. You burn the log in the fire, and what's left is a residue of matter that we call ash. You collect that ash up, and you measure its mass, and its mass is significantly less than the original log. And that's because matter was destroyed. Mass was consumed to fuel the energy that then radiated and dissipated, because it reached out to colder areas, but eventually brought everything in its surroundings to equilibrium. The simple implication of the law of thermodynamics is that the entire universe will eventually be converted to energy, more specifically, heat energy. What's interesting is long before we began this exploration into thermodynamics and understanding the heat flow of systems. And the biggest system of all is the universe, and it has subsystems within it, solar systems and subsystems within that, with every planetary body having that boundary of an atmosphere. But it's all keeps getting contained in a bigger and bigger system. And so the Bible actually gives us some insight to this in 2 Peter chapter 3. And so let's just observe a couple things from 2 Peter chapter 3, and let's look at verse 10. Here in verse 10 it tells us, "And the elements shall melt with fervent heat. The earth also and the works therein shall be burned up." Everything is being converted to energy. All matter will eventually be produced to heat energy. We get that right in the simple implications of the laws of thermodynamics. A couple verses later, 2 Peter 3:12, "The heavens being on fire shall be dissolved, and the elements shall melt with fervent heat." So again, everything is going to be dissolved. And what will be left, for a briefity anyways, is the heat energy that was produced. But once that energy is dissipated, once the universe is at equilibrium in the distribution of that heat energy, nothing moves. There is nothing left. God already knew that. God already told us about that. I suggest you Google at some time recurrence plot of mathematically generated chaos. Okay, they actually ran through a program and generated a plot graph, and we're all familiar with those. At some point in school, we had to make a plot graph in science or in math. And so it just taking a look at what chaos looks like. And there's nothing to graph. You can't connect the dots because they're everywhere. And they're everywhere randomly. It is mathematical chaos. And that's what we're moving towards. We're moving towards chaos. I'm going to leave you on the program today with something that was said by Paul Adrian Marcy Dirac. I may not have said his name right. He lived from 1902 to 1984. He was an English theological physicist who made fundamental contributions to the early development of both quantum mechanics and quantum electrodynamics, something above most of our heads altogether when we start getting into quantum physics. He was the Lucian Professor of Mathematics at the University of Cambridge. Pretty good university to be a professor at, has some renown. A member of the Center of Theological Studies, the University of Miami, and spent the last decade of his life at Florida State University. Among other discoveries, he formulated the Dirac equation, which describes the behavior of pheromones and predicted the existence of antimatter. Dirac shared the Nobel Prize in Physics for 1933 with Erwin Schwadring, I'm sure I pronounced that name incorrectly, for the discovery of new productive forms of atomic theory. So this guy is smart. This guy is a mathematician and a scientist of renowned caliber, a Nobel Prize winner in physics. He understands atomic theory and how the matter of the universe works and operates all the way down to the atomic level. He understands quantum mechanics and quantum electrodynamics. He has a vast source of knowledge. He also did work that forms the basis of modern attempts to reconcile general relativity with quantum mechanics. So he bridged scientific disciplines. He was regarded as one of the most significant physicists of the 20th century. Here's something he said. This brilliant scientist, as he examined the universe, as he was seeking a cause for the effects that he observed in physics and quantum mechanics and quantum electromechanics and atomic theory and relativity. A theory with mathematical beauty is more likely to be correct than an ugly one that fits some experimental data. God is a mathematician of a very high order, and he used very advanced mathematics in constructing the universe. This brilliant scientist who lived not so long ago, in the last century, in all of his vast knowledge and all of his vast research, his final conclusion was what? God is the brilliant mathematician that created the order of the universe and set it in motion. I hope you tune in next Sunday. We're going to pick up here at 9 a.m. on 106.1 The Flip in our investigation of how we can know the origin of the universe and how we can know for certain that God is behind it all. We're going to pick up next Sunday with fact number 2, the universe shows signs of design. Until then, I hope God blesses you and God keeps you, and I hope you join us again as we continue this exploration on cogitations.
Tune in next Sunday at 9 for another edition of Cogitations with Carl Hartman, minister at Main Street Church of Christ in Lockney.